So this is the technical video. Hopefully this is the last recording that we have to do, but clearly not, hopefully. But anyways, we're going to get into without further ado. So right, I'm KTK, and this video we are recording as a sort of technical basis for you guys to understand exactly what this robot is all about. The hardware design of the robot and the electronics design of the robot all come together in order to make the full design, and it took a lot of tries, frankly, in order to get this right. But hopefully you get sort of an idea as to what sort of research and development actually went into the making and the final creation of this robot as a whole. So this video is primarily going to be divided into two parts. The first part is going to talk about the hardware of the robot, which is going to be talked about by me, KTK, and the second part of this video is going to talk about the electronics and the software design of the robot, which is going to be talked by Satvik sitting over there across the camera. Anyways, without further ado, let's get into it. So, if you want to talk about the hardware design of the robot specifically, this is the robot right here, as you can see, and a lot of design and ideation went into the making of this robot. So, there are three aspects to the robot in total. If you want to talk about the hardware, the first is the electronics holding cage. The second part are the wheel drums, and the third part are the tire shells. So, let's start with talking about the electronics holding cage for once. The electronics holding cage is the module, as you can see, which is housed in the center of the robot. This here is the electronics holding cage. The front holds is a slit for the Raspberry Pi camera. Apart from that, the custom PCB is mounted on the top. The two motors are housed on either side of the robot, and the battery power banks are housed at the end of the robot right there. Right. So this electronics holding cage is responsible for being the main control unit of the robot. It is responsible for housing all the major aspects of what controls the robot, what actually makes it move. So in a sense of the matter, it is the main system and the main base from which the robot operates. Some of the more interesting features about this electronics holding cage is that we decided to keep the power bank and the LiPo battery pack at the bottom of the electronics holding cage, and this is specifically because we wanted the center of gravity of the electronics holding cage to be lower than the rest of the total cage design, right? So that helped it in self-balancing of the robot. What basically happens is that even if the electronics holding cage for example goes and topples at a certain cliff or a certain terrain disturbance, the electronics holding cage is going to be able to correct itself and ensure that the robot always comes to the same inertial position, and that is why the electronics holding cage is considered to be went through several so it is always going to be able to hold its inertial position. The electronics holding cage was also very difficult to design for us because it went through three different iterations, three different generations to be exact. And we will have them on the screen as we discuss. The first iteration allowed for the battery pack. We always had the idea of having the battery pack at the lowest rung of the EHC, and that was specifically because we wanted to ensure that the battery packs held the center of mass down in the cage. That resulted in the self-balancing aspect being fulfilled at the first behest. Right. So the first design, as you can see on the screen right here, was supposed to be exactly that. Just that the lithium polymer battery pack that in this design we have included just on top of the normal battery pack or normal power bank was supposed to be placed in the center of the EHC. So, but the problem with that essentially was that it made the EHC too big, too bulky, and there was too much material costs. We needed to optimize it in order to get a sort of better bang for our buck. And since we are Indian, we obviously needed a bang for our buck. We couldn't really afford it. We were cheap college students. That was one of the reasons for optimization of the first design. The second design was basically a similar design to the first design, first generation, but essentially the difference was that we changed the orientation of the placement of the battery pack, as you can see in your screen on your screen right here. Yeah, so in essence the difference was basically that we made the battery placement from vertical to horizontal, and that's basically it. That was because we wanted to sort of ensure that the robot could fit in all the components very well and the wheel drums could accommodate the electronics holding cage. But yeah, that resulted eventually in a third design. So basically we went to said axis in order to get this robot part printed, and we found out that the EHC was using tons of support structure. In fact, if you were to consider 100% of the print of the ESC, 50% of the ESC which was being printed was just the support structure, and it was equal to the actual ESC in weight. And we didn't really want that, because that made us use a ton of more material than we were required to. Also, the case was that it greatly increased the cost. So what we did was is that we ran a series of optimization brainstorming sessions on it, and we eventually came up with this final design, which you can see right here. And this design is great in the fact that it allows for the placement of the batteries at the bottom. It allows for the cable management to be better, because the cables just escape from the bottom, and there is space behind, as you can see, that allows the motors to connect directly to the motor driver, which is mounted right here. Inside which there is space for the Raspberry Pi, and on top there is obviously the mounting space for the PCB. So that resulted in a very optimized electronics holding cage structure being designed by us. And yeah, so this was the final iteration of the electronics holding cage. Two more things to be added in the electronics holding cage, since we want to talk about a little bit more about the optimization. So the motors which you can see right here are DC motors which operate at 60 RPM and rated for 12 volts as the maximum amount of voltage. And this was not the initial motors that we decided to use, and so we sort of went into a sunken cost fallacy, and we were going to be using BLDC motors, which the ones which you probably use when you're designing a drone or something like that, and that sort of motors which are used for the propellers of that drone, because we already had access to those motors and we didn't want to spend too much money in buying those new motors. But that turned out to be a very bad decision in the long run, since the wheels couldn't move at all. Since the RPM, although it was very high, we needed much more power for the wheels to actually overcome the friction and start moving. So yeah, this was a last minute decision, and this here right here is an example of what an engineer can do when pushed to the brink of deadlines. And the amount of hot glue that we used in gluing these two motors to the wheel drums was really pretentious, if I may say so myself. So this was the total optimization and the final production of the electronics holding cage. Now we will move on to the wheel drums. Right. What are the wheel drums? The wheel drums are the intermediary which you can see right here. These are the drums which connect directly to the tire shells on top, which is the third part of the robot. The wheel drums were important in the fact that they allowed us to actually isolate the tires inside of the tire shells from the rest of the robot, provided a sort of barrier between the EHC and the tire shells. Also acted as a sort of support structure while attaching the tire shells to the ESC in the first place, because we needed a way to mount the motors, and this provided us a medium to help us mount the motors effectively. Why were the wheel drums important? The wheel drums, as I said, helped to connect the tire shells to the motor mounts, were the intermediary. Yes, and designing that also took about 3 tries. So in the first iteration of the wheel drum which we planned to make, it was not really a wheel drum at all. It was just a sort of axle which connected directly to the end of the tire shell, like just through the rod here, just a rod through here directly connected to the tire shell, and you'll see that picture up on your screen right there. Yeah, so the thing that it did not allow for us to do is that it sort of made us worried that if we were to print this sort of iteration of the axle, as we would like to call this first generation of the wheel drum, the axle would allow for flexing in the shaft between the tire shell and the motor mount, and that is something that we did not want, considering the robot was significantly heavy and it was significantly bigger than this when he first started out anyway, right? So because of that, we had to redesign the wheel drum, and the second iteration of the wheel drum was essentially like a lid on top of a jar, right? It did not have the spokes as you can see right here. It was totally flat with just a full final covering. The idea was that we could essentially isolate it from the inside environment of the tire shells. But the problem was is that it took too much material, it cost too much money for us, and we couldn't afford that. So what we decided to do is we decided to put in spokes, make it more like a wheel, so that it could be worthy of the name of the wheel drum, right? And we significantly used less material. So eventually at the end it was supposed to be covered by a plastic sheet here and here, but because we couldn't really find the plastic sheet and we forgot to buy it, we ended up not covering it, and that's the simple problems that you might encounter while making your great project. So that sort of plastic covering allowed us to incorporate vision integrated technology, or VIT as we call it in short, no pun intended. Moving on, that was in fact the design of the wheel drum, and this is the third and final iteration, and yeah, we will move forward to the most important, one of the possibly the most important aspects of the robot, which is the tire shell. Now, why is a tire shell important, right? The whole premise of this robot was to build a standard model for space exploration. Now, the tire shell allowed a way for us to have extra storage space, as you can see, right inside here. It allowed us also to put on top modular connections so that it could traverse in different sorts of terrain. Now, obviously, you can see that we don't have that, and that is because, the simple answer is we didn't have money. And I'm going to continue repeating that again and again because it's something that is very worth to mention here. Anyway, so as you can see, it was supposed to cover this, and the idea basically was that even if the robot lands on its side like this, it would always be able to correct itself and land on its feet. With the electronics holding cage also returning to its initial position because of the self-balancing aspect of it, this robot is special in the sense that it does not need a gyroscope at all. Although we have added one just for extra measure, why not, right? Anyway, so it will always come and balance itself in the same inertial position that it's supposed to, and the camera will always face forward and it will never fall, theoretically. Right, and that is part of what makes this robot actually that great. So this is the tire shell, and in the tire shell what we have added are 2 to 3 things that we want you to see. First of all, these coverings which you can see on this is a tape, and on top this is a covering here. This is what you call polyurethane plaster, and it's essentially the same thing which you put on your leg if your leg is broken. Now, why did we use this? You already have your answer, so I'm not going to repeat it. But anyway, this was supposed to cover the entire length, the entire shell of the robot. However, we didn't have enough plaster at the end, so we weren't able to fully cover it. However, what this allows us to do is sort of give us a padding. So even though the screws right here, they go up top, and there's a nut on top. And because of that nut, the robot finds it difficult to actually move in space because it does not really get a flat surface to roll and move on. What this polyurethane plaster does is actually give some padding so that we can put the grip tape on, and the robot has got a flat surface to move so that it actually grips the ground and moves forward, backward, left and right as you want it to. And you can see the videos in the playlist down below of it being operated. So basically what we did was that we printed out the tire shells, we put a polyurethane padding over it, and on top we put a grip tape so that it could have enough grip in order to move in on the ground while having enough grip. Yeah, so this is the design of the MOON, the moon, or the Mobile Orb for Omnidirectional Navigation. Now, why are you explaining this all to you? This is because this design is totally unique. This sort of pill-like, capsule-like robot design has not been made anywhere in the world. And the fact is that people are going to call you out and say that, oh, just make something that has already been made. But yeah, try to make something different. We tried to make something from scratch. In a literature survey, we could never find an aspect of a robot that was supposed to be in this sort of model. And we made something different, we made something new, and we made something from scratch. And that is the best part about this robot. And hopefully this inspires you to make your robot or whatever you're making, which is something new in the world and not something which you copy off from the internet or something that you might see online. Make something which you think from your mind. Anyways, so this is the hardware aspect of the robot. And now Satvik will come in the next half of the video where he talks about the PCB and the software aspect of the mobile or for omnidirectional navigation.
Hi, this is Satvik Sumanta, and now we are going to discuss about the electronics and software design of the Project Moon, that is Mobile Orb for Omnidirectional Navigation. As you may know, that electronics is technically the most important part of a robotic system. It is the nothing but brain of any electronic system, you can say. So in this circuitry, we have many components and a custom designed PCB. So if you want to know like how you can design a PCB and what software we use the open source software named KiCad. KiCad is an open source and free to use software tool which is used for designing PCBs, printed circuit boards, by DIY and hobbyist people, and also even in industries. So this software provides you easy to use tools and pre-built libraries where you can use the symbols, the footprints required for your project. So as you may see, this is the PCB which we have had made for our project. Okay, so you can see the designs of the circuit layout we have given, and even you can put your symbols, logos, etc. And like as you can see here, we have the signatures of mine and Karthikeya. So that is how it goes. So let's further talk about the components which we have used. The most important part is of a robot is its processor and controllers. So in this we are using a microcontroller which is the Arduino Nano, which has the microcontroller chip at Mega 32. So this is basically controlling all the sensors and the motors. So after that we have also deployed a IMU sensor, which is a MPU 9050 sensor. This MPU 9050 sensor is a 9-axis sensor which has 3 axes of gyroscope, 3 axes of accelerometer, and 3 axes of magnetometer. Apart from that, this particular model of MPU 9050 with sensor which we are using, it also has a barometer module BMP 085, which you can use to measure the air pressure in the environment and calculate the altitude from the sea level, which we are currently on. For us in Chennai, the sea level altitude is 7 meters. So if anyone is trying to calibrate their projects regarding barometric readings, your correct answer would be 7 meters, and keep a margin of error for yourself. Apart from that, we also have a GPS sensor, which is the Neo 6M GPS sensor. It is a very user-friendly GPS sensor. You can find all about it over the internet. There are multiple explanatory videos on the YouTube as well. And then there's a temperature and humidity sensor called DHT11. That is another environmental sensor which we have used on this robots as a payload. So DHT11 was used to measure the temperature and humidity in the air. Then we have a micro SD card reader. So this micro SD card reader was particularly involved in our system for data logging and data backup. Even though we have a data transmission system, which I will tell you later, this data logging is very important in any project. If somehow someday your project fails, you will have some kind of black box which is holding your data, and you can recheck as to what happened that day of failure. So that is a very important task. And even if you are always transmitting data and you are technically logging it, but there are moments when data transmission can break. So you need a backup of your data. So like if you say, let's say for 5 minutes your robot was out of communication, and luckily the robot wasn't damaged, but then you can ask the robot to send you the data it saved in that backup files, and you can then calibrate and measure the changes, what happened and what caused the investigation can be done to find the cause of connection breakage. And for the communication module, and for communication, we have used two modules, which are HMC05, that is a Bluetooth communication module, and for a long range communication, we have used a NRF24L01 radio transmission. So both these Bluetooth module and the radio module, Bluetooth is the HC05 and radio is the NRF24L01. So both of these work on the 2.4 gigahertz frequency range. Why 2.4? Because it is the common open to use frequency. Your Wi-Fi, your phone Wi-Fi, hotspot, routers, these work on 2.4 and 5 gigahertz. So there are no licensing issues for you if you are going for a DIY project. And we have majorly worked with Bluetooth. There are issues working with the radio systems of the NRF module. So you may have some issues. So you need to just go through some quick searches and all. And then, since all the components cannot be directly provided power via the lithium polymer battery, because it has a very huge voltage, and Arduino Nano is incapable of giving constant voltage and current to all the parts simultaneously. So you will need to use a voltage regulator. So in this system, you can see there are two voltage regulators. One is a 5 volt regulator and one is a 3.3 volt regulator. The 5 volt regulator is of the serial number L7805, and the 3.3 voltage regulator goes with the serial number LD1117V33. LD1117V33. That is for the 3.3 voltage regulator. That is easily available in the market or in any electronic shop. These things are must to be used. So by using them, and you must read a datasheet when designing any electronics component. Please read the datasheet. That is the most fundamental thing to do before touching in electronics when you are making complex circuits. If you are going just directly putting sensors, not a problem if you are one sensor, two sensor. But when you are making voltage management or power system management, so then the datasheet for these ICs, these MOSFETs are required to get the correct circuitry which will be required in your system. And these are provided by the manufacturers of these components. So in our case, we found these data sheets very easily on internet, and the circuits were made using appropriate values of capacitors, so to filter out the signal and noise in the circuit, etc, etc. And talking about the software, the graphical user interface, which was developed and named Probe Data Acquisition, PDA GUI. So this particular PDA software was made and was made using the tkinter library in Python, and we were recording the data in our laptop by connecting the HC05 Bluetooth module to by pairing it to the laptop. So in this case, when you pair HC05 or HC06 if you are using, so a COM port gets open. In our case it was COM4, COM5, it can be anything for you, just check the device manager. So these COM ports are open for data reading. So using PySerial libraries, we were able to fetch the data which we were sending in a comma separated value. So A, B, C, that was the particular data format which we were sending. It was not a CSV file, it was just a CSV sort of notation. So temperature, humidity, longitude, latitude, number of satellites, etc. That's how we were fetching the data. And then it was being read in the Python, and mat.lib was used to show the graphs and all. And for camera, the most important, as you can see, here is a camera slot. The ribbon cable will be coming here, and then there is a camera holder. You may not see it in the video right now because we have removed it, and we submitted to some person who had helped us in the development of this robot. Thanks to that guy. Now Arduino is not able to support camera. It has a very low RAM, 2 kbs of RAM, so that is not enough. So in our first generation of circuit design, we had the plan to use OV760 camera module. So that is a very common camera module that is compatible with Arduino, but the flaw in that, it is consuming too much RAM. You will get, in the best case, if you somehow extend the RAM, by adding an external RAM IC to the Arduino. Then you can push it to 10 frames in some videos I have seen. But and it also has 18 pins in it. It's just baseless, and because putting 18 pins in Arduino, which alone has 30 pins, you just lose all the pin connections, and you will where will you put your other sensors and all, because each sensor needs 3 to 4 pins. So we then let go of the idea of using OV760, and then we went to the idea of using a Raspberry Pi Rev 1.3 camera, which is a 5 megapixel camera. And for this particular Rev 1.3 camera, 5 megapixel quality, we used a Raspberry Pi 02W. It is a 512 MB Raspberry Pi, and we put a 32 GB micro SD card in that as the main memory of the Raspberry Pi. 32 GB main memory, and then we have a 512 MB of RAM. So this is quite a good range of RAM to operate a camera, and Rev 1.3 has been designed. You will get a ribbon cable, you just plug it, play it. Simple. Many videos available, you can go through them. So that is regarding the camera system. So now, how do you take the camera images to the laptop? So what we did in the Raspberry Pi, we made a server client model where server was the Raspberry Pi and client was our laptop, which acted as the mainframe. So in this server client model, we developed a server code which was fetching the camera frames, and then via socket programming, it was giving the frames to our mainframe computer, and we were able to watch the live feed from the robot. And on the other hand, Bluetooth transmission was giving us the sensor values regarding various things like satellite data regarding longitude, latitude, temperature data, and barometric data, acceleration data, magnetometric data, gyroscopic data. So these were being given by the Bluetooth module. So thank you for listening, guys, and do take care that even if you may have not done something regarding electronics, it is easy. Just keep reading those things, keep reading the manuals. So you may be a very good software engineer, you are trying to do a hardware project, your friends may be helping you, but take an initiative to read the data sheets first. If you do not, you can burn the components, you can hurt yourself, money is wasted, you are hurt, everything goes south. So that should not happen. Safety first, and keep working hard, and just make anything you want. Thank you.